Oops, hello statistics and pre-calculus. So welcome to your first video in topic 7. So we're doing 7.1, finding rational solutions of polynomial equations. We're going to do that by first developing the rational zero theorem, which sounds really fancy and isn't really that fancy. So let's just take a look at an example and dive right in. So we have this polynomial. It is in a commonly known form. You should know this by now. It is intercept form. Awesome. So in intercept form, we can tell a lot of things just by looking at the polynomial. We can tell the degree. See if you can figure out what the degree of this one is. All right, so the degree is 3. 3 factors all raised to the first power. We can tell if we have points of tangency. Do we have any points of tangency here? If you said no, you're correct. All 3 of our factors are raised to an odd power, so we have no points of tangency at each x-intercept. We're going to cross the x-axis. Finally, we can tell end behavior, positive or negative graph. Positive. If it's positive, does it end in sort of like the right top quadrant or the right bottom quadrant? So it's going to end in the right bottom quadrant. And we know because it's odd that our domain is going to be all real numbers, and so is our range. So we're not going to have a restricted domain like we would if it were an even function. So perhaps most importantly, from this, we can tell where our x-intercepts are. So our x-intercepts are at, oops, and I'm so sorry for my dog in the background. Our x-intercepts are at x equals -2, oops, -2, +1, and -3. So at this point, this is all review. So now we're going to get into some new stuff. So first things first, we're going to translate this from intercept form to standard form. To do that, you basically are just going to FOIL out this whole thing, right? So I went ahead and did this ahead of time just to save time, but if you want to practice foiling, press pause on the video now and then come back when I have the answer. So the answer is x cubed plus 4x squared plus x minus 6. So we'll make this a little bigger so we can look at it now. Something that you may notice if you're looking really carefully is that our x-intercepts all are factors of this number here. So the last number in our polynomial in standard form is 6, and our x-intercepts are -2, 1, and -3. Now think about what the factors of 6 are. We have 1 and 6, and we have 2 and 3. Interesting, right? That's all I'm going to say for now. Next example. So this is not purely intercept form, right, guys? So this is a little bit more complicated. And to do this, we're actually going to have to find our x-intercepts here. We're going to have to set each of these factors equal to 0 and solve for x in each case. So go ahead and do that. Pause the video if you need to. And I, meanwhile, will go ahead and give you the answers. So your first intercept should have been -3/2. Your next intercept should have been +5/4. And your third intercept should have been +1/6. So hope you all got that. Again, that should have been review. So we are going to move on. So these are our intercepts, right? Once again, we need to put this guy in standard form. So I will go ahead and give you the answer. Once again, pause this video if you want to practice your foiling. Otherwise, g of x equals 48x cubed plus 4x squared minus 92x plus 15. So I hope you guys got that. Oh my goodness, that's all in the subscript, isn't it? Whoops. Minus 92x plus 15. All right, that's a little better. Okay, so like we did last time, we're going to try to see if we can see any patterns in our x-intercepts, and they're a little hard to pick up at first, so I'm just going to kind of be spoiler for you and tell you that in the numerators of all 3 of our fractions, we have the numbers -3, 5, and 1. What these all have in common is that they are all factors of 15, right? So we have -3, so -3 times -5 would be 15. +5 times +3 would also be 15, and 1 times 15 is 15. And the denominators of all 3 of these guys, 2, 4, and 6 are all factors of this guy here, 48. So what have we learned, right? So at this point, what we've learned is that the numerators of our zeros, right, are the factors of the constant term. So your constant term is your guy that doesn't have an x by it or that has x raised to the 0 power by it. So in this case, 15. In this case, that was 6. And the denominator of your zeros is going to be a factor of your leading coefficient. So in this case, it was 48, which is why we had some wacky answers. And here, our leading coefficient was 1, so we had these nice whole numbers. All right, so you have just derived the rational zero theorem. So here we say, given a polynomial p of x with a zero m over n, m is a factor of the constant term, and n is the factor of the leading coefficient. Cool? Let's just look at it graphically just to make sure you get it. So if you are an astute observer, you will notice, and I'm going to go ahead and move my video up, that these are the two graphs we just looked at plotted. Alrighty, so you can see right away, in this one we can see our x-intercepts are 3, -2, and 1. That's pretty easy, right? Once again though, this one is a little tricky. I'm seeing, okay, I have one that looks like it's between -1 and -2, one that looks like it's between 0 and 1 but closer to 0, and one that's between 1 and 2 and closer to 1. So you would be able to look at this one and say, well, I know that I'm going to have x-intercepts, right, that are going to be divided by some factor of 48. So maybe that's why they're so small, and that's why they're so funky too. So you would be able to look at this and kind of know that you have a polynomial that's leading coefficient isn't 1. Whereas if you were given a polynomial that looks like this, you know right away that 1 is your leading coefficient because you have all nice whole numbers for your x-intercepts. All right, so that's all we're going to say so far. Today you basically just derived your zero theorem and proved to yourself that it's true. Next time we're going to actually use that zero theorem to find some zeros. So stick around.